let's get existential here. What is 2? What does it mean to be 2 or not be 2? Like, really think about it, and don't use the word 2 in your definition.
Interesting.
For clarification, is it the number?
It's a squiggly line looking like a question mark with a straight line on underneath it.
It kind of looks like a guy who's had a really bad alcohol experience and he's praying to the porcelain gods.
Only even prime number, which makes it amazing.
Good answer.
Yeah, it's not a prime.
Excuse me?
The only even prime number. The first even number.
The one even prime number.
Not the first time that somebody who is doing this has mentioned that specific property. Maybe you watched my first 2 video and you remember that, or you're just...
Did you force me to watch it?
It's more than just having one of something. It is 1 plus 1.
You all got a 1 and a 1, and boom, that's 2.
Boom.
It's a combination of singular parts. A couple of singular parts.
Are you kind of saying like 1 plus 1?
Yeah, so it's 1 plus 1.
You have one of something, but then you have another of that same something. Is that just another word for 2?
I don't know if you knew that, but 1 plus 1 is 2. I think your viewers should learn that.
I'm going to have some responses to these so you guys can amend your answers, get a little better, but...
I stand by what I said.
4 minus... No. 5 minus 3. Square root of 4.
Square root of 4, okay. Those are just like examples of numerical expressions that get you there.
Well, I would say it's just a quantitative description of something pertaining to a pair of objects. So if you have a singular kilometer, 2 kilometers is a pair of kilometers.
Well, then what at that point is 1?
A singular thingy.
A singular thingy.
It's a unit. It's a standard unit thing.
Like the next question could be, what is 1 then?
It's a number that represents the quantity of objects.
No, it's any number, actually.
Yeah, so it's one object.
But is that suggesting that the only way that we can have 2 of something is if that they're like exact replicas or clones of each other?
I think that does suggest that, so the definition needs to go a bit further then.
Because then that would counteract your example of 2 coasters, but they're not exact clones of each other. They're within a relative category of things that you can place your drinks on, right? Coasters.
2 people.
2 people. This is 2 right here.
Not clones.
We have a you, and then we have a me. Does that, since we're not clones or replicas of each other, I mean, you're my sister, but does that mean that we're not 2 people?
Depends on what the unit is. If you're asking for 2 humans, we fit them.
You can have more than one human, but we're not all the same. We're not all clones of each other. Or you can have like different apples and things like that.
Apple and orange?
Apple and orange, okay. So, can we compare apples to oranges, though?
No, we can't compare apples to oranges, but we can have an apple and an orange, and then we have a 2.
2
We
what?
have 2 fruit.
This is 2 coasters, right? I think he thinks I'm wrong.
I don't think that he thinks you're wrong.
Okay.
I think he just wants more.
Okay, some more.
A pink flower, but I also have a red flower. So I have more than one flower, but they fit the same category of flower, but they're slightly different.
I'm seeing a pattern here. It seems that people can't come up with a definition without using an example involving units. Go ahead and hold up the coasters again.
I would love to.
You're giving me a set of objects. No, that's 3.
Yeah,
that's
'cause
too
you
many.
said you wanted more.
We have a set of objects within our relative category, and you could have just as easily given me 2 similar objects, like 2 trees or 2 buttock cheeks. But these are just examples of representations of the number 2 using relatable units. This shows us that without a proper unit in context, numbers are just an abstraction in which we can't relate to. Without using the relative units,
Numbers mean
they really don't mean anything. However, I just wanted the number 2.
Man, that's deep.
I think that's incredibly difficult to describe without using units. It's like trying to tell a blind person what red looks like.
Is there a right answer?
And you are allowed to shamelessly give up if you can't think any further than this.
Man. Yeah, I think because I just think of it in terms of like units.
Sometimes they went towards the number line for help.
It is the number that comes after 1.
Cool.
It is behind 3.
Here they're referencing numbers around 2 to help define it, even if they're not directly saying the number 2.
And we're talking about whole numbers.
We're talking about whole numbers, yeah. Because what about fractions or decimals?
The average of 1 and 3.
In between 1 and 3, what's the midpoint of that line
The
segment?
midpoint between 1 and 3. Yeah. Number line. Yep.
So,
I like it.
in any case, the number line is ascending, right? Is it? Here we go. I've been getting used to having to do a mirror image when it comes to my videos, so I'm not quite sure what you're seeing. But if I were to use the same logic and define the number 3, using numbers like 2 and 4.
Yeah, I don't like that because then you have to think about what is a number in general, and 3 is just the same as 2. What is it?
So I used the number 2 to define 3, and you used the number 3 to define 2. So that's circular logic. So at what point do numbers have any meaning? Whoa! Whoa! Whoa!
Numbers are arbitrary. Math is a social construct. We all live in a simulation.
Oh.
Thanks for coming to my TED Talk.
It's just an abstract thing that we can only use like relational things to kind of describe it, and it's a made-up construct. It's a human construct, so it's like time, It gives us a way to, picture things and how to communicate things with each other,
That's interesting. You're making it towards a societal construct, a conventional way to, as you said, communicate with each other. You hit the nail on the head there. Math is something that humans have created. It's a language that we've used to communicate with each other.
It's a language we've used to communicate with each other numerically.
I feel like somebody famous once said that numbers are the universal language. And I feel like that's part of the definition.
So I don't want a definition using units, and I also want to avoid using the number line. So what's left? The idea is numbers can be used to describe any scenario, figure it out what the calculations are, and then you can apply the proper units in context of a real-world scenario. But that's kind of what led me to my answer. Turns out I used pieces of both ideas and put them together in a more general form. My answer is kind of convoluted in a way, but my best answer is the set or family. The family of all sets that contains this many elements. Yeah, I'm not using the word two, but like let's unpack that. A set is just a collection, a group of things, and an element is just a member of that group. We want all of the sets that have this many things. And each of those interior sets can have a loose definition of what counts as that. The problem with trying to define these numbers, like this works for any number, is like when we first used numbers as a society, we used them in like trade and bartering.
Right. Mm-hmm.
To determine, okay, I'm gonna give you 2 chickens for your block of salt. In grade school, we just kind of had it drilled in our head that we go 1, 2, 3, 4, 5.
There was no relationship as far as what it was. It was just, this is how you count.
Mm-hmm. Without a relative, like a relatable example,
it's just a word.
1 orange plus 1 apple equals 2 fruits. Those are categories that we have established as a society to be relatable enough to be an acceptable conversation. You can use the statement of 1 plus 1 equals 2 for anything, right? Like any units. So it could be 2 black cats. It could be 2 cats. It could be 2 animals, 2 living things, 2 things. They could be as broad or as specific as you want. There's near infinite possibilities for examples, and all of them contribute to our abstract concept that is...
2.
2?
2.
The number 2. Now that we have a better idea on what the number 2 even is, let's count by using it. 2, 4, 6, 8. Who do we appreciate? 2? Not counting by 2s, but counting using base 2. So when we count, we always count. When we learned to count, we know about 10 different symbols. 0, 1, 2, 3, you know the rest. When we go through all of the symbols, we run out, then carry over to the next digit, and then start over again. When you learned this number 10, you probably thought of it as 10 ones. But for now, I want you to think of it as 1 10. I kind of said the same thing with a little bit of a nuance, but hold on to that thought. Trust me, it's going to help later on. Then we continue on, this one increasing through the symbols until we have to carry over to the further next digit. This conventional system is called the decimal system because the prefix DEC refers to the number 10. But what if we only had 2 symbols per place value? Try this with me. Take your hands and hold up the number 0. That was pretty cool, but I'm ready to move on to the next number, which we all know as 1. Okay, I know we can do this, guys. Moving on to the next number, I guess we can hold up a number 2, right? Wrong! We already used the 2 symbols that I said we had to start with, 0 and 1. So what do we do next? Well, last time, when we ran out of symbols, we moved on to the next digit. And that's no different here. So we go 0, 1, then we ran out of symbols, so we reset and carry over to the next digit. This looks like our 10, but in base 2, this is equivalent to the number 2, and we still call it 2. Good, so to keep going on with this, we go to the next number, which we call 3. Then we want to go to 4, so we have to reset this, carry over, reset this, and then we have to go to... I ran out of hands. Let's see if I can splice this. Perfect. This is number 4 in base 2, because this place value is no longer 100, it is a 4. So then the place values are going to be 1, 2, 4, 8. So by construction, the next place value is named after the next integer exponent of 2. Exactly the same way that we do in base 10, we just have a different number of symbols that we're restricted to. I'm sure you've heard that computer language is a bunch of zeros and ones. Well, this is why. It's much easier for computers to talk in binary because it views the number as a bunch of ons and offs instead. In fact, the power button on some electronic devices is secretly a 1 and a 0 for exactly this reason. The next clip I want to show you is from a show called Futurama, and it might be my favorite show. The creator, David X. Cohen, actually has a math degree, and besides the show being just funny in its own right, its co-creator Matt Groening is the creator of The Simpsons. But David likes to put in little math Easter eggs for people like me to get really excited about.
No doubt about it. This place is haunted.
Don't be silly, mon. The last ghost died over 200 years ago.
The last human ghost. But robot ghosts. Ah! What?
0101100101. What does it mean?
It's just gibberish. 10100111010. Ah!
When I first watched this episode, I was happy not really paying attention to the number and instead appreciating the joke for what it was. Binary number, and then in its mirrored image it means something. But one day I got curious. Why was Bender so afraid of this number? Well, let's see what it's equal to. Let's convert it from binary to decimal. This is a lot more place values than the 3 we were working with earlier. In fact, where does this go up to? Let's see. Starting at 1, and then times 2 is 2, times 2 is 4, 8, 64, 5, 12. It's not like I have my powers of 2 memorized or anything. These place values that I have written under here are the decimal equivalent to the value that the place value is worth. So like, we're used to doing ones, tens, hundreds, thousands, because those are the exponents of 10. Once you know what your place values represent, you simply just add them up. Wherever we see a 1, I'm going to bring that down here. If I want to do this in my head real quick, okay, plus 2 is 10, plus 16 is 26. 630, no, carry the 1, so 40. Lo and behold, it's the infamous 666. The number of the beast and the sacrifice. What's going on? I don't have the rights to play Iron Maiden songs. This moves us on to quick response, or QR codes. You know, those things with a bunch of dots on them and then the 3 squares and you can scan it with your dumb phone and it takes you to a different website. These things are everywhere nowadays. It's quite simple in construction, and I wouldn't be surprised if it replaced the barcode soon enough. You know, if you think about all of the applications that it has, you begin to wonder, will we ever run out of unique codes? Let's think of it this way. Each place where a dot or a pixel could be is a representation of a binary place value, meaning it can be an on or an off. Question, how many configurations are there in a code with, let's say, 3 place values? Looks like there's 8, and that makes sense. Each place value has 2 different modes, and there's 3 different place values, so that's 2 times 2 times 2, which is 8. This is 2 to the 3rd power, and in general, every code is going to be 2 to the x, where x is the number of pixels we have to work with. Now let's apply this concept to an entire code. There are 3 squares that are just for alignment and orientation purposes, and then there's lines that connect each of them for timing purposes. So all of these pixels are fixed. They're going to be the same no matter what code you use. I'm using the smallest one for emphasis, but there are much larger codes. These codes are 21 pixels long and 21 pixels high. So 21 times 21 is 441, and removing the orientation squares and the buffer zones is 3 times 8 times 8, and the 2 timing lines of each of size 5. We have 239 pixels to work with that makes each code its own special snowflake. So that's 2 to the 239 different configurations, which is this monstrosity. To put this into perspective, let's start by watching this video explaining how large 52 factorial is. And this number is famous for being the number of unique arrangements that a deck of cards has. Here's the kicker though. 2 to the 239 is 11,000 times larger than 52 factorial. So you can go to sleep in your jam jams knowing that we'll never run out of QR codes. And here, on this most glorious day of 2s, February 22nd, 2022, which is on a Tuesday, I feel compelled to do something momentous. Excuse me.